Welcome to our final project presentation on analyzing an electric power system using network science. Our team, consisting of Fajardo, Fula, and Garzon, conducted this project as a part of the Network Science for Data Analytics course at the National University of Colombia. Our goal was to use the IEEE 118 bus system to identify vulnerable nodes and links in the electrical network and determine optimal locations for deploying microgrids. By doing so, we aim to provide valuable insights into the behavior of the electrical network and inform decision-making processes related to microgrid deployment and improving the network's resiliency. However, certain analyses, such as node embedding or similarity algorithms, are not applicable to the network type and application we are working with, and have been excluded from our analysis. We analyzed the IEEE 118 bus system dataset, which consists of 118 buses and 186 transmission branches. To perform our analysis, we utilized tools such as Panda Power for data handling and power flow simulation, NetworkX for network analysis, and Cytoscape for visualization and community detection. We followed a network science approach for vulnerability analysis, overcoming the challenges of simulating individual element removals in large networks. We explored edge vulnerability, node vulnerability, and community detection as our analysis approaches. For edge vulnerability, we considered centrality measures like edge betweenness and edge current flow betweenness, also known as random walk betweenness, that measures how many times an edge appears and random walks between all vertex pairs in the graph. Surprisingly, we observed no correlation between the considered centrality measures and the unserved energy on buses following the removal of each edge. However, this phenomenon was observed when considering the network as unweighted. To explore this further, we conducted experiments by assigning weights to each edge based on the power flow information obtained from the simulation. The introduction of the edge weights based on the power flow simulation proved to be crucial within this weighted context. The edge current flow betweenness centrality emerged as a promising measure. Interestingly, we found that the smaller values of this centrality measure corresponded to higher values of the unserved energy on buses, indicating greater vulnerability. In our particular case, the edge current flow betweenness centrality effectively identified the top three most critical edges: line 6, line 7, and trafo 12. In node vulnerability analysis, we examined 8 centrality measures, including closeness, betweenness, page rank, and degree. To determine the most critical nodes, we adopted a consensus approach, combining the top 10 nodes from each centrality measure. The identified critical nodes are: following the simulation of the impact caused by the removal of these buses, we made several significant observations. This node represents the external grid, and its presence is essential for conducting power flow simulation in Panda Power because it serves as a reference. These nodes exhibit critical behavior when measuring the total change in voltage magnitude at various buses after their removal. Their absence significantly affects the voltage levels in the network. These nodes demonstrate criticality in terms of unserved energy when they are removed. Their absence results in a notable increase in unserved energy within the network. This particular node holds significant influence over the network connectivity. Removing it causes a cascade effect, leading to the loss of functionality in multiple other buses. Additionally, We applied community detection using Modulant to identify groups of nodes with strong interconnections. This approach provided valuable insights into node vulnerability and highlighted critical nodes within the network. The following nodes were found to be important within their respective communities by considering its betweenness centrality. Notably, several of these nodes also appeared in the network vulnerability analysis conducted earlier, reinforcing the effectiveness of this technique in identifying critical nodes within the network. Additionally, nodes 8, 88, 24, and 60 demonstrated criticality when considering the total change in apparent power. This finding indicates that these nodes played a significant role in power flow dynamics and are crucial for maintaining system stability. Our study emphasized the importance of considering network structure and community detection alongside centrality measures in vulnerability analysis. These approaches provided comprehensive insight into system vulnerabilities, critical components, and optimal microgrid deployment locations. Although the considered analysis may not always provide precise results, they offered a valuable approach, especially when it becomes unfeasible to analyze the complete network due to its size. In complex power networks, the exponential growth of elements makes it impractical to conduct exhaustive evaluations. It's all. Thank you for your attention.